So this is 3.1 college algebra, starting on page 254, polynomial functions and models. So just a couple things that we're going to look at. When we have a polynomial such as f of x equals x squared minus 2x minus 3. Just a couple bits of vocabulary here. The number in front here is called the leading coefficient. In this case it's 1. This entire thing, 1x squared, would be called our leading term. It's the first term. And the degree of the polynomial function is, in this case it's 2, because it's got the highest exponent there. If I had a y in here too, let's say I had a y cubed, then the degree of this polynomial would be 5. You would add the exponents of the leading term together and get the degree of the polynomial that way. So this polynomial here, one of the things that we did in the last chapter was to take a polynomial and make some decisions or determinations of this. So if you were to factor this, you'd get x plus 1 and x minus 3. So your x value, or your zeros then, would be negative 1 and 3. Our x-intercepts would be negative 1, 0, and 3, 0. So we're just taking our x values and putting zeros by them. That gives me my two places where it crosses the x-axis. My y-intercept would be this number right here, negative 3, and 0 obviously would be my first term. My minimum value, because the graph does go like this, so I've got a minimum value, and my minimum value would be your negative b over 2a and function of negative b over 2a. So that would give you your minimum value. Your domain would be all real numbers. So let's go ahead and make this graph. Looks something like that. Be all real numbers, left and right. Your range would be always your minimum, which in this case is negative 4. So your range would start here and go up to infinity. So it would be negative 4 inclusive positive infinity. So anyway, that's the basics there from what we did in chapters 1 and 2. Let's look at a cubic function here for a minute. So when I factor this cubic function, I get x plus 4, x plus 1, and x minus 3, which gives me zeros of negative 4, negative 1, and positive 3, which then gives me my intercepts of those. That's a 0. And it gives me a y-intercept of negative 12. And I'm looking on page 255, the second graph. Gives me a relative minimum, relative maximum, and your domain. And notice when I say relative, if you look at the picture, there's my minimum, there's my maximum relative to what we've got right here. Okay, we're not looking down here and we're not looking down up here. We're not looking at the ends parts. We're just looking at what's going on right in here. And that's the maximum, and that would be the minimum. The domain, obviously, this distance to this distance. And my range would be starting down here in infinity, going up. Even though it curves back down, it goes back up to infinity. So that would give you your domain and your range. And if you look on page 256, it gives you some polynomial functions and some non-polynomial functions. Now notice the polynomial functions that are in green there. They're smooth curves and there's no holes. They are continuous. There's no breaks. Whereas when you look at the non-polynomial functions, you have, what would I say, sharp corners. And another thing you have is you have holes or breaks in some of these, like on the second one over, your h of x equals the square root of x plus 1 minus 1. It doesn't go any further than -1 to the left. It just stops there. But so it does not include, the domain does not include all numbers to the left, because from -1 to -infinity, it's not in the graph. A polynomial function from left to right will always be -infinity to +infinity, like the row above when they're all the green ones. Notice the one on the far right. There are some points that are not included there. It looks like maybe between 1 and 2 there's some points that are not included in the graph. So it's very possible that I have maybe 2 asymptotes there that the line doesn't cross. So anyway, those are some things to look at. And if you look at the bottom, it gives you some other. A continuous function is a function that continues. It does not have any stopping points or breaking points or holes. But if you look at the middle one and the one on the right, there are holes in there. The graphs stop and start somewhere else. In the one on the far right, the sine wave there, it's got a hole. It's got a little circle there in the middle of the graph, meaning that point is not included in the graph. So it's got a hole there, which means it is not a continuous function. It's a discontinuous function. Okay. So, the top of page 257, the leading term test. I had mentioned this in the past, that on the left and the right of our polynomial, as x gets very large or as x gets very small, as it approaches positive infinity or negative infinity, that area is referred to as the end behavior. What's going on at the end of the graph? So if I have a graph that maybe does this, I may not be interested in this stuff right here. I may just be interested in what's going on over here and what's going on over here. What is happening on both ends of this graph? Well, the leading term of a polynomial function determines what's going on in the end behavior. So if you look down below, we have the leading term highlighted in red, and then you can look at the graph and see if you can discover some general patterns that's happening there. So like when x is x squared, when the leading term is negative x to the fourth, when the leading term is 1/2 x to the sixth. So there's even degrees when you have exponents that are even numbers, and you have odd degrees when the exponents are, of course, odd. And if you turn to page 258, there's some tests that you can do in order to find out what's going on as far as end behavior. So let's look at that for a minute. Okay, so what I have here is the leading term test from page 258, and then I took some leading terms. So if you look at example 1 on 258, it actually has example 1a, f of x equals 3x to the fourth minus 2x cubed plus 3. Well, all we're interested in is the leading term, so I just wrote down the 3x to the fourth. In B, it gives you this long polynomial, and I just put down the leading term, negative 5x cubed. So let's look here and see what we've got. So according to the leading term test, if my exponent is even, which is the case here, and my number, right here, my 3, is positive, so I've got an even exponent and a positive number right here. My 3 is positive. When that's the case, I get a graph whose end behavior goes like this. We don't care what's in the middle. That's what these squiggly lines mean. I mean, there's something that goes on here. We don't really care what goes on. We just want to find out what's going on. So it's more of a polynomial or a parabola-ish looking thing here. We don't know. I mean, it could just go, it could do all kinds of crazy stuff in here, but as long as the end behavior does what we want it to do, we're okay. So an even number with a positive sign right here, okay, gives us that. So the next one, B, negative 5x cubed, gives us an odd exponent and a negative. So we look over here and see I've written on here an odd and negative, and it will tell me what in the world my graph is going to look like. So it's going to look something like this. So it could be that it looks like this, or like that. All we know is at the end it does this and it does this. That's all we care about. Okay, so let's look at the next one. We have x to the fifth. So we have an odd exponent and a positive number in front of the x. So an odd exponent and a positive number in front of the x gives me something that looks like this. Odd, positive. So not too hard. The next one is negative x to the sixth. That gives us an even with a negative number in front of the x. So it's going to look something like this. So that graph could actually look like this. So it can look any way you want as long as the end behavior looks like that, which is what we have right there. Okay, so you should be able to just look at the lead term and make those decisions on what's going on there. Okay. Okay, this is example 2. And what they're saying is consider this polynomial function here. And it says determine whether each of the numbers 2 and negative 5 is a 0 of p of x. So what we're trying to find out is when we graph this equation, does the graph cross the x-axis at 2 and negative 5? Okay, real easy way to do that. When we put 2 in here, or if we put negative 5 in here, what has to happen is we're talking about the zeros of a function. We're talking about where this graph crosses the x-axis. So if what we're interested in are the points that it crosses the x-axis, which in this it's going to be 3. How many points it crosses, that's great. What is the y value on every one of these? The y value is 0. So all we have to do to find out if the numbers 2 and negative 5 are zeros of the function is to put 2 in there. And if we put 2 in there, do we get 0 for our y value? Do we get 0 for our p of x? If we do, then that means it crosses at the x-axis. If it doesn't, it means it does not cross at the x-axis. Well, when we put 2 in there, we get a negative 7. So when we put 2 in there, we actually get a point down here of negative 7. Does not cross the x-axis there. If we were to put negative 5 in there, it does cross at the x-axis because negative 5 cubed plus negative 5 squared minus 17 times negative 5 plus 15 is going to give me 0. So that means this point right there crosses at the x value of negative 5, which I plugged in, and my y value being 0. So that tells me I do cross at 0. Okay, so notice what we have here. We have a polynomial that's expressed as a product of linear factors. So what we did is we took the polynomial and we broke it, we factored it down. Okay, so if you remember, my x equals 2 In fact, let's go ahead and do something here. Let's add another x minus 2 here, just following the example in the book. They have 3 x minus 2's. So my x value is 2, 2, negative 1, or 2. Those are the 4 possible answers that I get for this. That means that my x-axis, or my x-intercept, or my root, or my 0 of the equation is 2, 2, negative 1, and 2. I have 4 answers. Well, but because this occurs 3 times, I only need to show that it crosses at 2, negative 1. So sometimes when you have like an x to the 4th power and you're like, oh yeah, I'm going to get 4 answers, you will, but sometimes those 4 answers will be the same thing. And so then like this one, even though it's an x to the 4th power, you still only end up with 2 answers because one of those answers appeared 3 times. So hopefully that makes sense. If you look at the bottom of page 260, left-hand side, there's the graph of what I just put up there. Notice it crosses at 2, and it also crosses at negative 1. So even though it crosses at 2 3 times, since it crosses. You don't have to list it all 3 times. So what they did is they wrote this then at the bottom of page 260 as 5 times x minus 2 cubed times x plus 1. So what they did is they put this, this, and this all together and made it an x cubed. And they did that for a reason, which we'll get to in just a minute. If you look at example 4, they give us g of x. Let's do this in red. G of x. And they give us negative x minus 1 times x minus 1 times x plus 2 times x plus 2. And we can rewrite that as negative x minus 1, the quantity squared, x plus 2, the quantity squared. Okay, so if this were 0, then we could find out the x-intercepts. So x is going to be 1 when y is 0. X is going to be negative 2 when y is 0. Now, let's look at how many times the zeros of a function happen in both this example and this example here. Okay, we're going to look and see how many times it happens. Okay, x minus 2 occurs 3 times. X minus 1 occurs twice here, and it occurs twice here. Okay? In a case like this, we see that the 0 we obtain from this factor 2 has a multiplicity of 3. So what that means is it occurred 3 different times. 1, 2, 3. And that's why we put an exponent of 3 here. Okay? Notice that down here our x minus 1 occurred twice. So the x minus 1 has a multiplicity of 2, and the x plus 2, which occurs twice, has a multiplicity of 2. So zeros that have, let's go back up here, zeros that have odd multiplicities and even multiplicities are going to mean something totally different. So let's look at that for a sec. So if you look at the even and odd multiplicity in the middle of page 261, so let's just get kind of an idea of what's going on real quick. So let me get rid of all of, no, I don't want to get rid of all this. Let's make a little graph here. And let's look at the one I have circled there in red. So my graph looks something like that. So notice what happens when I have an odd number on my multiplicity. I've got a 1 there and a 3 there. If my multiplicity is an odd number, then my graph crosses the x-axis in those places that I have right here. if my number is even, like these two. Let's see if I can draw a graph over here, just a real little one here. What happens? The graph, top of page 261, looks like this. Notice here and here it touches the x-axis. It's actually supposed to touch, but it doesn't cross. So if my multiplicity is even, then the graph is tangent here. If the multiplicity is odd, then it will cross the x-axis. Okay, so let's go ahead and find the zeros, and we're going to use grouping here, and you already have learned how to do some grouping. So what we'll do is group these two together, and we'll group these two together. And we can factor out an x squared and have left x minus 2. And then we will also factor out a 9. And we're left with x minus 2. And then that leaves us with x squared minus 9 times x minus 2. And difference of 2 squares minus 3, x plus 3, x minus 2. So, by the principle of the zero products, the function, or the solution of the equation when f of x is 0 would be 3, negative 3, and positive 2. So those are the zeros of the function. Those are the places where the line of the graph crosses the x-axis. And I know it crosses it because my multiplicity, this is an odd number. And when those are odd numbers, it actually crosses. If one of them was even, then it would just be tangent to it and then would go back in another direction. Okay, so other factoring techniques can also be used. On the top of page 262, and they give you x to the fourth plus 4x squared minus 45. And this is where they do this. Oops. And they substitute u for x squared. And then they're able to go u squared plus 4u minus 45. And then they're going to solve for u. And then just go from there. So we've got what? U plus 9, U minus 5, and we're very easily, we can put our x squareds back in. And then that's where we get x squared plus 9 equals 0. And x squared minus 5 equals 0. So we have x squared equals 5. X squared equals negative 9. Take the square root of both sides. And you find out that, let's take this one, move it up here. We get x equals plus or minus the square root of negative 9, or plus or minus the square root, or I'm sorry, we'll take the square root of 9, and we get 3i. And when we do this one, we get x equals plus or minus the square root of 5. So I get that answer and that answer. 4 answers, and I have a 4 there. So those are my zeros of that polynomial. So only the real number zeros of the function correspond to the x-intercepts. So that being the case, then I know that this one doesn't correspond and I can't graph it. The square root of, or plus or minus the square root of 5 can be graphed. So I will get a figure that looks like the one on the left side column on page 262. So every polynomial function of degree n, with n being greater than 1, has at least one zero and at most n zeros. So that means that you will always have a number between 1 and 4 places that it crosses the x-axis. So notice, I got 4 answers, plus or minus 3i, plus or minus the square root of 5, which matches with the 4. But these can't be graphed, so that means that the equation only crosses the x-axis at these 2 points. So even though we got 4 answers, like I've said, you're going to get that match that. When you graph, you can only graph 2 of these. So it appears like there's only 2 places that you're only going to get 2 answers, but that's because it only crosses at the square root of 5 and the negative square root of 5 because of the imaginary number. So don't let that confuse you too bad. So that's it for 3.1.